So what do we need these robust tests for? The problem is that one-directional tests, like the tests that we've seen so far, the LM error, LM lag, LM SLX, or as I called it, LMWX, have power against other alternatives. What does that mean? It means that they will reject the null when the cause for rejecting the null is not what you're actually looking for. So you run a test for lag, it rejects the null, and you say, it's lag. But it isn't lag, it's error. And so each of these tests, the LM error test, the LM lag test, and even the LMWX test, they're affected by the presence of the other alternative. So the real case is an error case. You run a lag test and we reject the null, you say, it's lag. It isn't lag, it's error. How do you fix that problem? And this is where this notion of robust test comes into play. And again, as you can see, it's from the 1990s. As I mentioned the other day, it's a very narrow sense of what robust means. It means robust to local misspecifications in the form of another alternative. So local means not very much. Okay, so you do the test, there's a little bit of error, and you correct for that little bit of error to make sure that what you conclude is lag and is actually correct. Or the other way around, you correct for a little bit of lag to make sure that your error test is correct and rejects in the right direction. So that's the overall objective, is that at the end of the day, we come with a conclusion that is actually the one that we should be making. If we just run the simple, as I call them, simple tests, you may be wrong. So you run a lag test, you say, it's a lag model, but it isn't. And same for an error model, you think it's an error model, but it isn't, okay? So Berat and Yoon came up with this correction of the LM test, which they call a robust LM test. It's a correction that makes the test smaller. And the way to think about this, or at least I like to do intuitively, is that you take out a little bit of the effect of the other cause. So you take the test for lag and you get a value, say 8, right? And you take out a little bit of what of this 8 might be due to error instead of lag. So then the 8 becomes 6. Then the question is the 6 still significant? And if it is, then you conclude, it has to be a lag, right? That's the idea. Now, how you get there, that's another story. The math is pretty complicated. It has to do with local approximations and stuff like that. I won't go into specifics, but you'll see that all these robust tests start with the original test and take something out and make some other kind of scale correction. Now, there's a problem. And the problem is called the 2 out of 3 problem. So in the old days, the main models were lag and error, as I mentioned the other day. Then, since the 2010 roughly, the spatial Durbin model is all the rage. And that's a model that has both a lag term and an SLX term. The problem is that the original robust tests corrected for the presence of the other alternative. So in the context of lag and error, it was always just error or just lag. When you go into the spatial Durbin world, everything changes because it's now lag and SLX, or SLX and lag. Ideally, you would want to test, say for lag, that corrects for both possible error and possible SLX, which brings us to the GNS model. Remember, the generalized nested model has everything. has a lag, has SLX, and has error autocorrelation. So then the logic would be, just like in all the other cases, you start with the log likelihood for the GNS model, you get these partial derivatives and you get the scores and all that stuff, and then you can do the corrections. The problem is the GNS model in a maximum likelihood world is not identified. So you can't do it. So there's no way to correct one of these LM tests for both possible causes of other misspecification. You can only take 2 out of the 3. So the 2 are either lag and error or lag and SLX. As a result, the lag and error tests cannot pick up a spatial Durbin alternative. And the lag and SLX tests cannot pick up a spatial error alternative. So it's not an ideal world. And as we'll see in the lab notes, it can lead to very confusing empirical evidence. My rule of thumb is whenever the robust test is not smaller than the original test, a red flag should go up. You should start thinking, this can't be. The test is supposed to correct for something else. It's supposed to be smaller, not larger. Now, why can it be larger? Because you correct for the wrong thing. If the real other effect is error and you correct for SLX, then you correct for the wrong thing, and vice versa. So that is the 2 out of 3 problem. Very recent paper. I think it's not even out yet. I have a preprint. So it's not possible to develop a 3-way robust LM test. You can only be robust to one or the other of the possible alternatives. And of course, in empirical practice, you have no idea which the true alternative is. You don't know. Right? So you don't know whether you're correcting for the right possible alternative. You could be correcting for the wrong one, and you have no idea. What I say to that is, well, that's maybe a little too strong, because whenever you see weird stuff, then you have some idea. Then you know this shouldn't be. And why is it? Because something you're assuming is not right, right? You're correcting for the wrong thing, or you're estimating a model that doesn't actually fit the data, and so on and so on, right? So always, as I always say, it's very easy to do these estimations mechanically. You just click, 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 you got it. Interpreting it is not something you should do mechanically. Look at the coefficients. Do they have the right sign? Do they conform to Tobler's law, which means distance decay? Your neighbor should not be more important than you. If it is, you better have a very good theoretical reason. I mean, it's always possible for in some phenomenon, your neighbor somehow is bigger or whatever, it's possible, but it's not likely. This Tobler's law, even though it's a little bit controversial, it's not called the first law of geography for nothing. It's a very strong empirical baseline that basically most phenomena show positive spatial autocorrelation. And there's a distance decay. Further things, less so. Right? And as we've seen, but not formally yet, to get these estimation methods to work, we need distance decay. If we don't have distance decay, then we don't end up with a situation where we have enough information so that we can mimic uncorrelatedness. See, we don't have lack of correlation. Our samples are correlated, which means they have less information. But if we go far enough apart, of course, that means we need a bigger sample, then we get the information back, as long as we're far enough apart. If you don't have distance decay, that doesn't work, okay? So it's something to keep in mind when you get weird results. And luckily, in the examples I use, they're a little bit contrived, admittedly, in the notebooks, but that's for a reason, because it is to show you weird stuff can happen, right? And you might say, well, it's because you have a contrived model. Fine, I'll take that. But I just want you to show you that it can happen. And in other words, the textbook result does not necessarily hold. Okay. There is a very complex but very non-standard result that I already alluded to last time. In most cases where you have nested alternatives in mathematical statistics or econometrics, a joint test is the sum of the two one-directional tests. In this case, that is not what happens. So the joint test here for rho and lambda is not the sum of the one-directional test for rho, or this is gamma, of rho and the one-directional test for gamma. Oh, no, it's not gamma, it's lambda. So this is the lag and error case. This is the lag test, this is the error test. The joint test is actually, and this is a very curious result, but you can trace it mathematically why this happens. The joint test is the sum of one and the robust form of the other one. So the joint test for lag and error is either the sum of the error test and the robust lag test, or of the lag test and the robust error test. It's very peculiar. The first time my colleague Anil Bera saw that, he's now a spatial guy. He wasn't a spatial guy. He couldn't believe it. He thought something was wrong. Okay, it's not wrong. And then in the spatial Durbin, same thing. So the joint test of the lag and the gamma coefficient is the sum of the one-directional test and the robust form for the other one, and vice versa. Which actually turns out to be really useful. If you recall, you probably don't, but you can look it up. These tests are very complicated in the spatial Durbin case. The joint test it's complex, but it's relatively easy to compute. The corrected test, the robust form, is extremely complicated to compute. So we actually don't compute it in spreg. We get the joint test, and we just subtract the other one-directional test, which gives us the robust form that we're interested in, because we rely on this property. Okay. And here we get with the complicated stuff. So for the notation, you have to go back to the previous set of slides. This is the robust test for error, robust to lag. You see here, this is the original error score, and you subtract something, right? And this is T, this is all these traces of W, W prime, W, and so on. And all this stuff gives you a chi-square with 1 degree of freedom. So this is actually complicated to compute, but you just click a button and it comes out, right? You don't have to worry about it. Here again, you see you start with the lag one, you subtract the error one, so you correct the original one for something else, and that again gives you a chi-square of 1. So now we have a battery of 5 tests for each of 2 cases. One case is the lag error case, or SAR error case, where we have LM lag, robust LM lag, robust to possible presence of error. We have LM error, robust LM error, robust to possible presence of lag. And we have joint lag and error. That's 5. Then in the spatial Durbin case, we have another 5. We have LM SLX and LM SLX robust to lag. We have LM lag, which is the same one as before, but the robust form is now robust to SLX, not robust to error. So it's different. And then we have the joint test. So 5 and 5, 10 tests based on the Lagrange multiplier or the score principle, Rao's score principle, that are based simply on the results of least squares regression. So no spatial regression involved, just least squares. And those tests can be used in a specification search. In fact, they will, in many cases, guide you towards which is the proper alternative. Okay. So in spatial Durbin, as I already mentioned, we don't actually compute them. I mean, you can. If you go back to the Coley-Berra article, you can see the complexity of the expressions, but we cheat. We take the joint one, we take the one directional one, and get this as a difference. So that's very easy to do. Okay. Now we're good. We have all these things. We have Moran-Xi. We have 10 Lagrange multiplier tests for spatial effects. And then we, of course, have heteroscedasticity and all this other stuff, which for now we ignore. So what I want to show you now is how this actually works in practice. And I'm going to assess the empirical power of a test. And there's two important concepts here, which you may not be familiar with. One is the bias of a test. A p-value is your decision criterion. In other words, if you do the test under the null, so there's no spatial effect, if you do this many, many times, how many times would you reject the null anyway? That is your p-value. So if your p-value is 0.05, you would reject the null in 5% of the cases, even though the null is correct. That's your type 1 error. That's the chance of being wrong, basically. That's the way I like to think of it. So the null is correct, but you reject it. But not very often. That's set by your p-value, right? So the smaller the p-value, the fewer you're going to reject the null when you shouldn't have, right? But that has consequences because it has to do with the power of the test, which is kind of sort of the complement, is how well do you reject it when the alternative is present. It should say reject the null when the alternative is present. That's a typo. So you reject the null. So if, let's say, we have a lag model and the spatial coefficient is 0.5, and you reject the null 100% of the cases, you're doing really well. If you only reject the null 20% of the cases, that's not that great, because you'd be wrong a lot of times. So two important concepts. The power of the test is how well do you do when you have a problem? And the bias of the test is how do you do when you don't have a problem? So the empirical bias, this is empirically, how often do you reject a null when you shouldn't have? And then the power is also empirically based. How often do you reject the null when you should, right? And the way you set this up is similar to what we've done before. So if you recall, we created different spatial models that generated a Y. Then we ran an OLS regression and saw what it did to the beta, right? Now we're going to do something very similar. We're going to generate a model with a Y. We're going to run an OLS regression and then use the residuals of that regression in a test. And then we'll see how often do we reject a null. And we're going to change the spatial parameter. For example, in a spatial lag model, we start with 0, rho is 0. That will give us the bias. And then we start cranking up the rho, 0.1, 0.2, 0.3, 0.4. And we run, say, 1,000 replications. How often do we reject a null with our test? And that gives us what is called a power function. So the power function gives us, on the horizontal axis, the parameter we're interested in. The parameter we reject the null for as that parameter changes. And on the vertical axis, we have the frequency of rejection. Ideally, if the parameter is not 0, we want that to be 100%. It's not going to be 100%. Okay, what does this look like? First, we look at the power against a lag alternative. So what I'm going to do is generate data for a spatial lag model. I'm going to slowly change the value of rho. For each value of rho, I'm going to run 1,000 of these experiments, look at my test, and record whether the test rejects the null or not at a given p-value, right? It's always at a given p-value. So this is the first set of power functions. On the horizontal axis, this is 0. So this rejection percentage is the bias of the test. Okay, in this particular case, I use 0.05. You know, if you eyeball it, this is roughly 1/4 of that distance. So we're pretty much on target. Then as rho increases, we see that these curves shoot up. Okay? And the ones most to the left, this one, is already basically at more than 90% for 0.1. Very small value of rho. And these two curves are the LM lag and the robust LM lag. So they do really well in this idealized case. They have very high power, even against very small values of the spatial lag coefficient. Okay. The next best is these two. And one of them is Moran's I, which really has no business rejecting the lag alternative because it's designed to pick up error dependence, and the LM error model, which also has no business rejecting the lag model, but it does. This is what I was talking about with the robust tests. The reason you want that is you want to take out some of this statistic that is due to the other alternatives. And that's what this purple line is. This purple line is the robust LM error line. And this one moves up much slower. Here, we're at 0.1, we're roughly already at 50% rejection, but we only reach 50% rejection with the robust form a little over 0.2. Right. This curve illustrates the correction that happens to the LM error test due to the possible presence of a lag alternative. In other words, there is a correction, but it's not that great. Even 4.3, which is not very much. I mean, we'll run some examples, and almost all the estimates are larger than 0.3. You have 100% rejection rate. So we have a real problem in practice in figuring out, based on these tests, what is the actual alternative? And we get around this problem by comparing the original test and the robust forms for all possible alternatives at the same time. So we actually really do use all 10 tests. You might say, why do you look at all 10? You should just look at one of them. It's exactly because of this. They all have very good power against especially lag alternatives. So this is one set. This is the second set. The second set, again, LM lag and robust LM lag. These are the leftmost. Identical curves to the previous graph. This is exactly the same thing. Here, the green one is the LM SLX parameter. So this tests for the wrong alternative. This tests for SLX, but in fact, it's a spatial lag model, and you reject the null almost 100% at 0.1 for the spatial lag model. So here again, the SLX test is unreliable because it will tell you it's an SLX model, whereas in fact, it should be a lag model. However, one thing does work somewhat is the robust form of the SLX test. So this is a spatial Durbin model. It's robust to the presence of lag. This is the presence of lag, and it gets moved to the right, which means it has less power than the original one when it comes to the lag. So the true alternative is the lag. We use the wrong test. How does it perform? The original one, you can't tell the difference. It will reject the null, even though it shouldn't, right? The corrected one does a little bit better, but not that great. It's better, but still at 0.4, you're at 100%. Right? So in particular, when the alternative is a lag model, you're in trouble. All these tests pick it up, even Moran's eye. Then you might say, well, what about the joint tests? Maybe they help us. Unfortunately, they don't. Again, these are the same graphs for LM lag and robust LM lag. And now we have the two joint tests, the one for lag and error together, and the one for lag for the spatial Durbin model. So lag and SLX together. And they're all pretty much track the same. So the joint tests, remember, the joint tests are really no good here because there's only one alternative. So there shouldn't be, in an ideal world, the joint test should not be significant. But you don't have two zeros. You only have 1 0, right? But they pick it up. And that's a downside of the joint tests. Again, this is not the usual result, but it is because these joint tests are not the sum of the two marginals. They're the sum of the marginal and the robust marginal. So all the classic results, or I should say, many of the classic results do not hold. The moral of the story is, if lag is your true alternative, you're in trouble. Because everything will reject a null, even the inappropriate null. Now, how are we doing when the true alternative is an error model? Again, same approach. We simulate the error model for different values of lambda, and we run the tests. We run OLS, and we run the tests 1,000 times. A little bit different. So we start with the lag tests. This is LM lag is the blue one, and the robust LM lag is the orange one. Oh, this is perfect. This is really good, right? So if we correct the lag test for the possible presence of error, it won't pick up the error. It's way down here. It will pick it up even when it's 0.9. It only will pick it up in a third of the cases, roughly. So that's pretty good result. These, not so much. Okay, so they all track Moran's eye, LM lag, and robust LM lag. They all track very well. Not quite as much power as the lag tests. You see the 100% rate is around 0.4. It's not around 0.2 or 0.1, but still pretty good, right? And the lag test has power, but not as much as in the other case. So the error case, in a sense, is weaker evidence of spatial correlation. The lag case is very strong evidence of spatial correlation, so every test picks it up. Here, less so. So now let's look at the other ones. The LMWX. Now, step back a second. The WX test tests for an SLX alternative. There is no SLX alternative, right? It's an error alternative. So this is what you would expect. It doesn't have a lot of power against the error alternative. It shouldn't. This is not what you would expect. This is the robust SLX test. The robust test should be worse than the original. It's actually better. Why is it better? Because you're correcting for the wrong other alternative. The robust SLX test is not robust to error autocorrelation, but it's robust to lag dependence. So you're correcting for the wrong thing, and you get weird results. We'll see that in the empirical illustration as well. Of course, here I know what the true model is. In the empirical illustration, I don't. Right? That's the difference. Typically, you want them to be like an S shape. This one is not. I mean, it might be, you know, eventually, but at 0.9, it hasn't even reached the top yet. So this green one shows very poor power.
So prefer higher power.
Yes. The more to the left is this left? Yeah. The more to the left this is, the better. The steeper it goes up, the better. Because that means it picks up even very small values of the parameter. Small, slightly different from 0. 0, you have the bias. Again, you know, around 5%.
Just want to clarify this, so the power means that if the error is the alternative, and I'm using like these kind of tests, what's the possibility that I can reject?
Yep.
Right?
So the power function, this is the frequency of rejection. This is the value of the alternative. This is the error parameter. So what this means is around here, you have 100% rejection for a value of lambda of 0.4.
I misheard you, but in the last slide, did you say that the orange one is perfect or something?
This one? So this one is, so the first slide is the alternative is the error alternative, and we use the lag test. The blue one is the lag test. So you see that again, there's the S shape. The lag test has power, but not nearly as much as the error tests, right? The robust lag test, the orange one, is robust to the presence of error. This is the presence of error. So it corrects. And it tells the lag test, this is not lag, this is error. Right? So you shouldn't be significant because you're pointing to a lag alternative, and that's not the proper alternative. That's how it works. So if you see the lag test and it says, oh, it rejects the null, it's got to be a lag model. The error test also rejects the null. It's got to be an error model. Then you look at the robust test. The robust error test still rejects the null. The robust lag test does not. Right?
So we want to make sure that the lag tests are used for lag.
Exactly. So, yeah, we want to make sure that the lag test points to lag when lag is the correct alternative. Here, lag is not the correct alternative. Here it's error.
It's p-value, right?
Not p-value, no. It's the percentage rejection, but using a given p-value. So you have to say, you know, you get a statistic, you get a number. What is the p-value? If it's less than 0.05, you reject, right? That's how it works. And then you count how often you do this, and that gives you the rejection frequency. And then finally, the joint tests, same problem. Doesn't help. They all have high power. So the joint tests are not actually that useful in this context, unlike what you may read in some papers. It doesn't work very well. They all have very good power, but you don't know which one it is. It could be lag, it could be error, it could be both, right? And then the last one is the SLX alternative. So now we have gamma on the bottom horizontal axes. The LMWX has good power. The robust one has none, which is not good. Okay, that was a surprise. So either I did something wrong or there's something funky going on there. But I've seen this in empirical results as well. And then the error test has some power, but the robust form does not. So that's good. This is good in the sense that, oh no, let me clarify. So again, this is the, this robust LMWX form is robust to a lag alternative. Okay. And so that may, in this case, there is no lag. So the correction is, I think, overkill.
Shit's weird.
It's weird, yeah. It does. It tells you it's no good. Even for very large values, you do not reject a null. You reject it even less than the p-value. Okay, this should not go down. So again, either I made a mistake, or something funky is going on. But we've seen this actually. We ran a lot of simulations. I'll cover this in the winter quarter when I talk about specification searches. And we've been seeing these kind of weird patterns. And this same thing here, the lag has good power against the WX alternative. But again, this robust WX is not doing the right thing. Okay. And then the joint tests, same. So the joint tests have, again, very good power against a single alternative. Okay. So the moral of the story is, don't get too excited, right? Interpret the results carefully. Only consider the robust tests when the original tests are significant. There is sometimes a tendency to, especially, you have to make sure you get a good intuition of what this notion of robust means. It's not better. Often robust means better, right? When we looked at the robust standard errors, the white standard errors and the hack standard errors, they were robust to things that we didn't consider before. So that's better, right? Here, robust is not necessarily better. Robust is in the sense of correcting for some other type of misspecification. But if you correct for the wrong other type of misspecification, you're not better at all. So be careful when interpreting this, especially if you find that the robust test statistics are larger than the original tests, something else is going on. And the joint tests are great because they pick up one-directional alternatives as well. They're not so great because they don't tell you that it's a two-parameter alternative. They have very good power against the one-directional alternative. So that doesn't help that one.